So today we start lecture 75 in our helicopter dynamics course, and today I'm going to discuss the helicopter force and moment equilibrium. I'm Dr. Ranjan Ganguly. Now, in many situations we need to calculate the helicopter forces and moment and find what are known as the trim control for the particular helicopter in equilibrium. So essentially, when the helicopter is flying, it is going to settle into a particular flight condition such that all these forces and moments sum to zero at the CG, and we want to calculate this particular position. Now, before we do that, let us look at some of the forces which can be obtained from the blade section loads, which we discussed when we tried to derive the different forces and moments in terms of the blade section. So let's look at thrust, for example. The thrust would be the Fz component, which is the vertical component, into dr, and this is integrated from 0 to r, and then you have d psi, and psi goes from 0 to 2 pi, and then you have n by 2 pi here. So this is actually summed over all the blades, n being the number of blades. Now similarly you obtain the H force in terms of Fx and Fr, and again the integration is performed with respect to r and with respect to psi. So these forces can be obtained. The y force can be obtained using this equation here, and the rotor torque can be obtained using this equation, and then finally from the rotor torque we can obtain the power required. So essentially these are some of the mean forces which are acting on the rotor. So at different sections there are going to be section forces, at different point on the azimuth there are going to be the local forces, and when we integrate all these forces we obtain the cumulative steady force which acts on the helicopter rotor. Now let's define some of the nomenclature which we are going to use to derive some of these equations. Now the condition of the rotor which is going to finally be there in space is going to be determined by the force and moment equilibrium on the entire helicopter. So before we go there, let's take a look at the rotor disc, and we have a certain velocity coming at the rotor, and this velocity is given by v. So now this v essentially can be split into two parts. One of them is in this direction here, and the second is in the vertical direction. So the vertical velocity would be equivalent to a climb velocity. So that would be Vc is V sine theta Fp. Now theta Fp is the flight path angle. So that's given by this value here. And so we'll look at this diagram in detail in the next slide. So this is a side view of the main rotor with the rotor forces. So as you can imagine, the velocity is coming here. This angle is theta Fp. This is alpha. So there is a thrust vector here. The angle here is alpha minus theta Fp. There is the weight of the helicopter. There is a drag. This drag is parallel to this velocity v. There is the H force. Again, this is at the angle given here. Then these are essentially all the longitudinal forces, and we are going to use this in deriving some of the equations. Now we can take a view from the back, and if we look at the helicopter rotor from the back, we have the weight here, we have the thrust vector, we have this thrust vector at some angle phi here, and we have the y force now. So again, remember that H and Y are the forces which act on the rotor disc or in the plane of the rotor disc. So Y is in this direction. There is also a force YF caused by the fuselage. So that's in this direction here. And these angles are essentially given by phi. Again, the weight is acting vertically downwards. So what we are going to do now is we are going to derive the equilibrium equations in some of these directions. So let's start with vertical equilibrium. So vertical equilibrium, we clearly see weight is acting downward. So this weight is going to be counterbalanced by, for example, the thrust. So there is a thrust into the cosine component of this angle here. That's this value. Then you have minus d into sine of this theta fp. That's this value here. Plus h into the sine of this value here. So this is the projection in the vertical direction. So essentially, this is the equation you have for vertical equilibrium of this vehicle or the rotor. Now, horizontal equilibrium can also be obtained. So in that case, let us look at D. So D would be into cos theta fp, that's this component. That would be plus h into cos of this angle here. So you see that term here. And this is going to be equal to thrust into sine of this angle. And so you see this here. So again, this equation would give you the horizontal balance of forces which is taking place in this particular rotor. Now we'll turn to the value of alpha which can be obtained by solving these two equations. So here I have written these two equations which was derived in the previous slides. The one for W and the one for D. And then we can solve these equations for alpha. So you'll have to do a lot of trigonometry here. And at the end of it, you can obtain an expression for alpha in terms of this expression here. Now, remember that all these forces have been obtained from the rotor sectional forces by integration, and the theta fp is known because theta fp is this particular value. So that's the angle at which v is coming. So this whole expression can be calculated, and therefore the alpha value can be obtained. So this is going to give us the orientation of the rotor disc, which is going to result as a result of all these forces which are acting on the rotor. Now let us look at the lateral equilibrium equation. So again, the rotor view is like this from the back, and now we can take the components. So we have yf plus y into cos of phi plus t into sine of phi. So all the components along this direction sum to 0, and vertically we would have w is equal to t cos of phi minus y into sine of phi. So we get two equations now. These two equations can be solved for phi. So using these two equations, we can obtain the equation for tan phi like this. And again, we know that all these forces, weight, thrust are known. Therefore, I can calculate the value of phi at which the rotor disc is there. And this is going to give me the angle between the axis here and the rotor disc, which is given by phi. So this again lets us calculate the orientation of the rotor disc in space. Now, what is left is yaw, and yaw is something which is very important, and probably we should have mentioned this a long time before in the course, but better late than never. So you have the rotor torque, and this torque needs to be balanced. So again, you all have seen the existence of the tail rotor, and the reason the tail rotor exists in conventional helicopter configuration is that this torque needs to be balanced by another torque. So this torque is created by the tail rotor thrust into the distance between this point at the main rotor and the tail rotor center. This we are calling XTR, or the location of the tail rotor with respect to the main rotor. So the equation we get for yaw is Q is TTR into XTR. And this essentially lets us calculate the value of the tail rotor thrust which should be there, XTR being a constant, to essentially balance the main rotor torque. So the torque created by the main rotor is countered by the thrust created by the tail rotor. That's a very important concept as far as conventional helicopters are concerned. Now, if you look at non-conventional configurations, then there are multiple rotors, and so there is a balancing possible using the multiple rotors. And in that case, the tail rotor may not be required, like in the case of the two main rotor systems, or in case of the systems with four main rotors or more. But there also the equilibrium has to be there with respect to all the rotors. Now, the tail rotor has only collective pitch theta Tr and no cyclic pitch. Therefore, the tail rotor thrust is completely controlled by the pilot by simply varying theta Tr. So that is one more of the control. So remember, the main rotor controls are theta 0, theta 1c, theta 1s. The tail rotor control is theta Tr. So these are the four controls which are in the hand of the pilot, or in case you are flying this helicopter using some control system, they are in the hand of the controller. So the four pilot controls are there: theta 0, theta 1c, theta 1s, theta tr, and we also saw that the rotor is in space and the tilt of the rotor is given by alpha and phi, and these can all be determined by solving the response and equilibrium equations. So essentially, whenever the rotor is given these controls theta 0, theta 1c, theta 1s, theta tr, then after some point in flight you are going to reach an equilibrium condition, and the alpha and phi are going to correspond to that particular equilibrium condition, and this entire set of angles is known as the trim solution. So essentially, moments are taken at the rotor hub so that the rotor forces do not enter into the problem. So let us look at some more possibilities in case the CG is concerned. So these are the equilibrium equations when we are considering the helicopter. So here we see that this is the rotor here, and the CG at some distance h below the rotor, and there is some distance xcg here, and there are some forces which are acting here on the helicopter CG. So we can write the equation my plus myf plus w into h alpha s minus xcg, which is the distance between the point here on the hub and the CG, and then minus h into d. So essentially that is going to give me the equilibrium for the longitudinal forces and moments as far as the helicopter is concerned. Similarly, I could obtain for the lateral forces, but before that let us just consider this equation. So again we are considering small angles here. The helicopter CG is located at a distance h below the hub and at a distance xcg forward of the shaft, and so we can solve for alpha s in this manner, and we are going to get this value in case the helicopter CG is located at some point xcg forward of the shaft and h below the hub. So all those dimensions are going to be known, and therefore I can calculate this quantity and I can obtain the value of alpha s. Similarly, I can calculate the value of phi s, and that would be given by mx here. The equation essentially is obtained by taking the moment. So we have mx, we have mxf, these are the two moments here, and the remaining moments are created by w h phi s minus ycg and minus yfh. So this is again assuming the angles are small, and therefore we can obtain this equation, and from this equation we can solve for phi s. So again we have solved for the equation phi s here, and as mentioned before, all these quantities, if they are known, the phi s value can be calculated, and these equations are valid for the CG at some location. So here the helicopter center of gravity is offset to the right of the rotor shaft by distance ycg, and so that's the ycg term here, and this is going to give you the value of phi subscript s. Now these expressions are very simple, and they do give us the attitude of the vehicle in a simple manner, and these are useful for estimate. So even when you have some complex helicopter code, the values which you can obtain by simple calculations by hand should be reasonably close to whatever you are getting from the complex code. Now, in numerical solution, all the six forces can be considered. The equations are more complex and more realistic, and you can essentially solve for the trim problem. So this is typically done using some Newton-Raphson method and so on, and you start with the estimate of the trim controls. This is typically obtained from rigid blade trim, and then you continue that process using the rigid blade trim starting values, and then the elastic blade is used, even the free wake model can be used, and you continue the Newton-Raphson procedure till you converge. So essentially a Jacobian matrix needs to be calculated in that case, and we need to perturb each of the control variables or the trim variables and calculate the Jacobian matrix. So that is something which is often done in a typical helicopter code. This lecture gives you a basic outline on this process as to how trim control calculation is an important part of the helicopter dynamics calculation, because remember that an accurate solution of the trim equations is required to calculate the response correctly and therefore calculate the helicopter loads, vibration, bending stresses, and so on. Because depending on the value of the different trim controls and the vehicle position, the loads are going to change on the flight vehicle. So I'll stop this lecture here and I will see you in a video sometime soon. See you then.